Hello, and welcome to lesson 10.1. Now, in class, this is a in-class lesson, so this is actually going to be a little bit longer than those short videos because I had to talk a lot today during class. But yeah, so this is the introduction to exponential and logarithmic functions. I printed these notes out in class, and so I'm just going to kind of go along and teach just like how I did today in class. So if you were absent or whatever, you can watch this to get refreshed on it, or maybe it didn't make sense the first time, so you just want to look again. Okay, so in Algebra 1, as I'm reading this right here, you kind of briefly learn about exponential functions. Now, I guess it kind of depends on your Algebra 1 teacher, but usually it's really a very short introduction to exponentials. You talk about the graph. By the way, here's a reminder. The graph looks like this. Okay, it starts off slow, grows really big. And it's defined, like 2 to the power of x. That's like an example of an exponential function. You do this in Algebra 1. You study some growth and decay functions. You learn how to write those functions to model real-world problems. And you look at the graphs and kind of analyze what's going on in the graphs and what information it tells you. But you don't do a whole lot of solving. You don't really deal with exponential equations and how to solve them or manipulate them. That is where we come in Algebra 2 to really expand upon that knowledge. So that's what we're doing. Now, this lesson, sometimes it's structured differently depending on your teacher. Sometimes in Algebra 2, teachers just go through exponential and then they introduce logs. Sometimes they do logs first and then they go through exponentials. I'm choosing this year to go through both at the same time. Because I think we have a really good understanding of function inverses, and so that might help build our understanding this year. Anyway, let me actually get on with the video here. So we are going to be talking about logarithmic functions, and I'll get to that in a second, but just know that they're very, very closely related to exponential, okay? But first, I'm going to go through some Algebra 1 reminders on the exponential functions. Stuff you should know, even if it's in the deep recesses of your brain. Once I write this out, you should be saying, oh, okay, I remember this. I've done this before, okay? All right. So a basic exponential function, we're talking, very, very basic exponential function with no transformations or anything like that, really, is written of the form y equals a times b to the power of x. This is our very basic exponential function. What defines an exponential function is putting the variable in the exponent. You see, x is in the exponent, right? And we have a few conditions on a and b. So first thing is we say that a is a real number. And I've used this notation before. It's just a reminder. That's a epsilon and then like a double-legged r. That means a belongs to the set of real numbers. It's just a way of saying a's a number, okay? Such that, such that a is not 0, okay? So that's all it is saying a is any number, it's just not 0, okay? That's it. If it were 0, you'd be multiplying the exponential function by 0. You get 0, and this function wouldn't be growing or decreasing at all. It wouldn't be doing anything. It'd just be staying at 0, so it would be pointless. One maybe quick thing to note that we do talk about in Algebra 1, when you have a basic function like this, you can quickly identify that a is the y-intercept. Okay, because if you put in 0 for x, it makes b to the power of 0 as 1, and so then a is the only thing left over, therefore a is your y-intercept. Now, if I do fun transformations, if I shift it left and right, up and down, stretching it, flipping it, everything like that, that's going to affect our y-intercept. So it's not always just that number in front. It's only if it looks really, really basic like this, okay? So careful with that thought. The next is b. And so we're going to say that b is also a real number, such that, and this has two requirements on b. B needs to be a positive number, so I'm going to say that it's greater than 0, not equal to, okay? It's got to be positive. Would be no point doing 0 to the power of x. It wouldn't do anything. And b is not 1. And this it would just be silly because look, 1 to the power of x. Put any exponent in there, you're going to get 1, okay? And that thing is not growing or decreasing or anything like that. So those are our requirements on b. You might ask, why does b have to be positive? Can't I do something like -3 to the x? Couldn't I do that? I say, of course you can, and then someday you will, but you'll find that isn't quite the exponential function you are thinking of. I'm not going to explain why b should be positive right now, and I'll leave that as a sort of thoughtful exercise for you to chew on, okay? But maybe at some point in class or in a video, I will talk about why that needs to be positive. We call b the base, so b is called the base. And often we say that b is the growth factor. I say and growth factor. And so this is just a reminder. We should know what that means. Well, why are we calling it a growth factor, right? Well, if exponential function either starts off really slow and then grows, or it shrinks and then decreases like so, right? So like it has a sharp decline and then it dies off slowly, okay? And so these are two different kinds of exponentials. So if your value of b is more than 1, okay, any whole number greater than 1, then this function represents exponential growth. It is a growth function because it increases. If, however, b is between 0 and 1, so it's a fraction like a half or 0.7, right? Then this function represents exponential decay. Now you're going to have a few homework questions that ask you to analyze what's going on with b. Now, again, these are all characteristics of this basic function, a times b to the x. Here's an example of why you need to be careful. If you say 1/3 to the power of x, that would be a exponential decay function because b is between 0 and 1. However, if you say 1/3 to the power of -x, that is actually not exponential decay. It actually becomes exponential growth. And that is because you have flipped the graph horizontally, if you know your function transformation. So all these things are saying they only are for this basic kind, okay? Once you introduce transformations, you need to be more careful in how you analyze these functions. Okay, so let's move on to a few examples here. The equation of the exponential parent function is y equals b to the x for any choice of b, provided that b is greater than 0 and b is not 1. So that's your parent function, okay? The most basic that you can be. It's not even with an a value. It's just some base to an exponent. You can choose what number to put in the base, okay? In this example 1, we're going to graph the parent function y equals 2 to the x, okay? And we're just going to quickly graph this. Now, we know how to graph things. In order to graph something, you just throw in points. Just throw things in for x and evaluate where the function is. Since it's a very basic parent function, I'm going to do the classic -2, -1, 0, 1, 2. this will just give me an idea of what this curve looks like, kind of in the middle, all right? If you even consider that this function has a middle, because it's not symmetrical. Anyway, let's graph this parent function. So I'm actually going to start from the far right here. It's not a 0. I'm just circling that so you see. I'm going to start from the far right. If y equals 2 to the power of 2, right, I'm plugging in 2 for x, that is 4. So 2 comma 4 is 1 point. And I'll say 2 comma 4. I'll put a point down. If I say y equals 2 to the 1, that's just 2. So 1 comma 2 is another point. If I say y equals 2 to the power of 0, remember, you have to know what power of 0 is. Any number to the power of 0 is 1. Of course, and as I say in class, there is a debate on whether 0 to the power of 0 equals 1, question mark. We've discussed that in class, and that's something you can investigate if you like. So that's 1. Now, what is y equals 2 to the negative 1? Now, you got to remember your negative exponent rules. I told you got to burn them into your brain. 2 to the power of negative 1 is 1 over 2 to the 1. So this is actually 1/2. So it's negative 1 comma a half. And then if I do y equals 2 to the negative 2, that's 1 over 2 squared. That's 1/4. So I'm going to zoom in here. Negative 2 comma 1/4. I'm going to try my best to make a little dot there. Okay? And you know what? Just for fun. Okay, just for fun. Whoop, I'm going to extend this little line here. Whoop, just for funsies. Let's put a 3 in here. Say y to the 2 to the power of 3. That's 8. So that's 8. And I'll just get another point here. 3 comma 8. All right. And so you can kind of see that general curve. You see it's growing really slowly, and then it's shooting up, right? And that is how our exponentials functions look like. So I'm going to erase all this. Now, I want you to think about what happens if I keep decreasing x. If x is negative 3, then negative 4, then negative 5, then negative 6, and so forth, right? Well, as you go to the right, you're doubling. Times 2, 8 times 2 is 16, 16 times 2 is 32, and so forth, right? But if you're going backwards, you're not doubling, you're halving, right? It's 1/2. Cut a half, if you cut a half in half, it's a fourth. Cut a fourth in half, you get 1/8. Cut an eighth in half, you get 1/16. Cut a 16 in half, you get 1/32. Cut that in half, you get 1/64, and so forth, right? And it's going to get really, 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 really small. And you think, well, what number is it approaching? What is it getting really close to? If you keep continually cutting that in half, you're minimizing it to about 0. However, it's never actually going to touch 0 because, well, if you're taking half of something, you'll always have some amount, right? So you're actually never going to touch 0. So recall, as we've talked about this word asymptote before, an asymptote is a line that the curve approaches, but it doesn't always touch it, right? In this case, it's not going to touch 0. So what I'm going to do is make a horizontal asymptote here on the x-axis at 0. That is the value of this function is approaching but not touching, okay? And so now I'm going to very carefully try to smoothly connect these curves. Oh, sorry, I want to make this really pretty. Ooh. That's a little too sharp. Let's just freehand it. Oh, that's nice. That's beautiful. So it's much easier to do this on paper than it is an iPad. I apologize. Okie doke. So there's our exponential function. That's what it looks like. Now let's maybe answer some of these questions. To say the asymptote, that's at y equals 0, because it's a flat horizontal one. X-intercept, well, it's not touching the x-axis, so there is none. The y-intercept we can very clearly see is at 0, 1. Our domain, notice the graph goes left and right forever. It's defined for all real numbers. We call that negative infinity to positive infinity. Or if you like, say that x is a real number. Okay? Either one is good. Range. Well, it's it's at 0 and going up, right? But it's not touching 0. So you say it's parentheses 0. It's not bracket. It's not inclusive because it doesn't actually touch 0. It doesn't equal 0, but it shoots on upward from there. Another way you could say this is y is greater than 0. Okay, that's both interval and inequality notation there. And that's just the parent function. That's all that is. We've already done this, guys. We've already graphed these functions, but I wanted to start with this so you feel strong, you feel comfortable, you feel confident, ready for what's to come, all right? Because if you can't graph this by hand, well, you need to be able to, okay? This is just the parent function. That's all it is. Okay, let's graph a more complicated function. So this one has a few transformations here. So I guess I'll just write it out. If you recall, we've done function transformations of a times f of b times x minus c plus d, right? How does this translate for an exponential function? And in this case, my base is 2, right? Base equals 2. So what does this look like? Well, you'd have an a value times your base in this case is 2, and the input is the exponent. So it's b to the x minus c in the numerator, and then plus d. So the vertical stretching and reflecting and the shifting factors are not in the exponent. They're affecting the function on the outside. The horizontal transformations are in the exponent, okay? Just so you can kind of see that. And you should already be familiar with A, B, C, and D. Okay, you should already know what those are because you've been doing them all year. Okay, if you're not sure, go look at Unit 1 on parent function transformations. So let's look at the transformations here. I've got a vertical stretch by 3. I should say by a factor of 3, but whatever. Because it's stretching the function by that. I'm multiplying the function by values of 3, so the y values are getting tripled in that regard, okay? Let's say to the power of x minus 1. Well, x minus 1 means it's a shift right by 1. And a minus 5 at the end means it's going to be moved down 5, okay? Those are your transformations. Now, you can take a lot of these points here and transform them like so. However, I'd be careful because of this stretch, okay? That's going to elongate your y values, meaning, well, you need to be, you could alter the values in this table, but honestly, I would just recommend starting from scratch, okay? Make a new table. So let's plug in some values. You can still do the -2, -1, 0, 1, 2 strategy. But what I like to do is I like to get a couple points sort of to the right of the middle. And when I say the middle, I kind of mean the y-intercept or just what looks like the center of the graph. But does the graph truly have a center? I guess not really. It's not symmetrical or nothing. But anyway. So here's what I'm going to do. I say, what makes the exponent 0, right? What makes x minus 1 equal to 0? 1, right? So I'm going to actually put that in the middle of my table here. I'm going to consider that that's the center because that's going to make, even though that may not be the y-intercept because x isn't 0, it is forcing the power to be 0, which is a nice number. So let's try this out. If I plug in 1, right? I plug in 1. Then I've got 3 times 2 to the 1 minus 1 minus 5. 2 to the 1 minus 1, that's 3 times 2 to the 0 minus 5. 2 to the 0 is 1, so that's 3 times 1 minus 5. That's 3 minus 5 is -2. And so that's one of my points right there. Okay, 1 comma negative 2. Like so. All right. Now change that 1. And I'm just going to increment it. Let's say 2 and then 3. So do 2 minus 1. So then it's 3 times 2 to the power of 1. That's actually now 3 times 2. So that's 6 minus 5, which is 1. So 2 comma 1 is my next point. Right here. And now I'll do 3. So I'll make this a 3, which makes this a 2. And so 2 squared is 4. You like how I'm just writing over what I have? 3 times 4 is 12. And 12 minus 5 is 7. So 3 comma 7 right here. Beautiful. Okay. And I'm going to erase all that junk. All right. And so you got 3 lovely points there. And honestly, that's enough. Okay. When it comes to quiz and test, I've told you only need 3 points on the graph. This does give a good estimate of how fast it's growing. It's nice. It's a good visualization. So this would be sufficient so long as you give me that asymptote. Okay. I am, however, going to keep going, help find the y-intercept and all that jazz. So I'm going to go down to 0, and I'm going to plug in negative 1 as well. So let's plug in 0. 3 times 2 to the 0 minus 1 minus 5. Well, that's 3 times 2 to the negative 1. And 2 to the negative 1 is a half. So you see this is 3 times a half. That's 3 halves minus 5 is 10 halves. That's negative 7 halves. And so that's actually our y-intercept. And you know that negative 7 halves, that's like negative 3.5. So at 0, it's negative 3.5. We're just going to eyeball that about right there. Okay, and I'm going to write the y-intercept as 0, comma, negative 7 halves. It's fine if you use a decimal. It's okay. I just would prefer a fraction like this, okay? For graphing purposes, I can totally understand if you want to use a mixed fraction. If you want to write that as negative 3.5, that's okay. It's really helpful to graph if you write it that way. And then we'll also do the next one. We'll say negative 1 minus 1. So that's 2 to the negative 2. So now this is 3 times 1 over 2 squared minus 5. So that's 3 times 1/4 minus 5, which is, so that's now 3/4 minus 5 would be 20/4. So this is actually going to give us negative 17/4, which incidentally, I think that's negative 4.25. Okay? So at negative 1, it's about negative 4 1/4 right there. And that's a nice, lovely point. Okay? And so this is giving us a nice, accurate picture of what the graph looks like just by plugging those points in. Okay? Now, where's our asymptote? You can keep decreasing this if you need to kind of figure out where the asymptote's going. But notice, it shifted down 5, right? It shifted down 5. So if the original is at 0, we'll move 0 down 5. You will find that the asymptote is now at negative 5. In particular, y equals negative 5. Okay? All right, and there's my curve. And so I'm just going to draw it like this. Carefully draw it up like that. Not too bad. Nice. And that's my exponential curve. The reason I like to get so many points is so I have a really good idea of what this graph looks like. The more points, the better. But do recall that my graphing expectations are just that you know where this stuff is, know how to find 3 points, and you're good. Okay, domain and range. Domain is all real numbers, if you can plainly see that. This is going to be true for all exponential functions, unless we restrict the domain somehow, okay? your range is starting at -5. So it's parenthesis -5 up to infinity. So you could say y is greater than -5 like this. Okay. You see it's at -5 and it's going up. So done. That's my range. And you might say, what's my x-intercept? Well, my x-intercept, it looks like it's about right there, right? That looks like the x-intercept. X-intercept is, I say, what? Right? What the heck is the x-intercept? Sorry, you know what? I'm going to rewrite that again. I don't even care because this video can be as long as I want it to be, because it's not required viewing. I'm going to say x-intercept is what? 1.9? Question mark? 1.8? Question mark? Who knows, right? We can't tell. Look at that. I don't know what that value is. So, I don't know. I don't know. I think it's about 1.9, maybe 1.8 or something, depending on my graph, but I have no idea. You might say, well, Mr. Spake, what do you mean? It obviously exists. It's not I'm not saying there's no x-intercept. I'm just saying I don't know where it is exactly. You say, how can you do that? I say, well, to find an x-intercept, you have to set the function equal to 0. You say 3 times 2 to the x minus 1 minus 5. You could add 5 over. You say 5 equals 3 times 2 to the x minus 1. What makes that true? You go ahead and solve that. Ha-ha. That is lesson 10.3. In lesson 10.3, we're going to talk about how you solve such an exponential equation. So we will get to a point where we are able to actually find a decimal approximation of the x-intercept that's very accurate. But right now, it's fine, okay? It's all right. You've analyzed most of the features. We're okay. All right. Let's move on now to logarithmic functions. Okay? This is the new thing. I fear how long this video is going to be. Well, whatever. It took up a lot of class time, so it's going to take up just as much video time. Okay. Logarithmic functions. So, what is this? What is a log, right? We call these logs, by the way. Okay, these are called logs. So, a logarithm is the blank function to exponentiation. So, we've talked in the past about x squared versus square root x, right? Where x squared makes a parabola, and then square root x makes a square root curve, which kind of looks like one of the legs of the parabola, but on its side, right? The same is true for something like 2 to the x and log base 2 of x, okay? A logarithm is what we call the inverse function to exponentiation. So much like square root is to x squared, log is to exponents. Okay, logarithms are used as the inverse function for exponents. And that's what they are by definition. Okay? I want you to notice what I bolded here. It says both logs and exponentials use the same base. So, if I have a base of 2 to the x, your corresponding logarithm function, that's the inverse, is going to have the same base of 2. Okay, they share that if they're inverses of each other. So how do we write these things? Well, we denote a general logarithmic function of a base b as f of x equals log base b of x. Okay, I want you to notice how I said that. I said log base b of x. When I say of x, think of it like f of x, right? This doesn't say log base b times x. That is not what that says. It is log base b is a sort of function. It is an operation. It is doing something to a number. And then the number that you're putting in is x. It's an input, all right? So it's a function. This looks a little odd. You may not have seen something like this before. It's the same as saying square root x, right? What is square root doing? Here's an example. If I ask you the square root of 16, you should say that that's 4. If I ask you the square root of 5, well, what would you say? You'd say the square root of 5 is the square root of 5, right? That's what it is. And you can get a decimal approximation with that if you use a calculator, right? Do you know how the calculator is doing that approximation? You probably have no idea unless you've learned how to do square roots by hand, which is very interesting, but also rather tedious. For the same reason, whatever's happening with a log, right? Whatever log is doing, log base b, let's call it like log base 2 of 5, right? That's going to be something you put into a calculator to tell you an answer, okay? It'll give you a decimal approximation. We're not going to figure out logs by hand if they aren't pretty. I will show you how you can evaluate logs when they are pretty, and you'll be able to identify when you're able to do that, okay? And he says, well, what are you talking about, pretty? You'll see, okay? You'll see what I mean. Anyway, a few more notation things. And this is classic stuff to know. A logarithm of base 10 is usually written without the base. So if I write log x, and you don't have to put the parentheses there. I usually do. I usually put parentheses around it like this to really identify what's the argument of the log, what's the input. I'm just going to write it log x is the same as log base 10 of x, okay? Those are the same thing. We usually don't write the 10. You're more than welcome to. And if it helps it keep you straight in your head, write the base 10 so you understand that. But if you don't see it, it doesn't mean there's no base. It just means that the base is 10. It's implied, okay? This is because we've worked with base 10 forever, just historically. We've always used base 10 for a lot of stuff. And so naturally, logarithms, we operated in base 10. Now, we can operate it in any other kind of base, log base 2, log base 3. But base 10 is a really common one. And when we first had calculators and log tables, they're all printed out and whatnot, they were in terms of base 10. The other common one is a logarithm of base e, okay? You say, well, what is that? The heck is that? If you're an Algebra 2 student for the first time, you might be looking at that letter saying, is that a variable? And I say, no, that's not a variable. E, this is called this. I want you to pause the video and read that out loud for your own sake. Okay, this is Euler's constant. And I say, Euler's constant. All right. You say, it's not Euler? No, it's pronounced Euler. Leonard, I think, is that his first name? Leonard Euler. Okay. Very famous mathematician. Oh my gosh. Such a famous fella. So important in the history of math. So Euler's constant is kind of like pi. It is a very special number, approximately 2.718. Oh, that's not a 1. 2.718. Okay? The decimals go on forever, just like pi, right? You know that pi equals 3.14. You should also know that e is 2.718. We use a 3 decimal approximation for e usually. The more decimals you have, the better, though, okay? but it's approximation. Okay, where does E come from? What is Euler's constant? How did this number come about? Save that question for another time. I am sure you can find a plethora of YouTube videos talking about what Euler's constant is, where it comes from, and the rich history behind it, because it really is beautiful. I mean, it's a beautiful number, okay? I don't have time to talk about it in this video. I'm so sorry, but maybe I'll make a video on it one day, okay? For now, E is a new number that you can burn into your head as 2.718, okay? When I have a logarithm of base E, I'm going to write this as ln of x, or ln x. And that is not an I, that's an L. It says the ln stands for natural log. That is what ln stands for. If I say, well, why not NL? Well, it's a Latin thing, okay? Well, I forget what the exact Latin thing is, but L came first and then N. But it means in English natural log. It is the logarithm of nature. And you say, well, why nature? E. And if you want to figure out why E has a connection to nature, go down that rabbit hole, because E is everything. It is natural growth. It is an amazing number. Anyway, just know that E is a number that pops up in nature all over the place. Hence, it is called natural log. Okay, here we go. So, from here in class, I taught this next part as sort of pattern recognition. So instead of just outright telling you what a log is, well, you know it's the inverse function, but what do they look like? How do we evaluate them and things like that? I just wrote a bunch of examples. And so I'm just going to mimic exactly what I did in class here now, okay? And I'm just going to go until you think you figured out the pattern. Log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of 8 is 3. Log base 3 of 84 is 4. Log base 3 of 1/9 is -2. Log base 3 of 1 is 0. Log of 100, I'm going to say 1,000. Log of 1,000 is 3. Log of 1/10 is -1. Log of, 1 again is 0. What other ones did I do? Oh, I think I did, log base 5 of 5 is 1. And log base 5 of square root 5 is 1/2. Okay. Did you figure out the pattern? Do you understand what's going on? If I encourage you to pause the video and really think about it before proceeding, because I will tell you what the pattern is. Okay, so what's going on here? Well, perhaps you're noticing a pattern here. Look at my base in this example, 2, 2, and 2. Those are all the three bases, right? Well, 2 to the power of 1 equals 2. And 2 to the power of 2 equals 4. And 2 to the power of 3 equals 8. And so are you seeing how it is 2 to the power of 1 equals 2? And then 2 to the power of 2 equals 4. And 2 to the power of 3 equals 8. So this kind of cycle A logarithm is an inverse of an exponent. Notice, when we say your input and your output, your x and y values, right? For inverses, your input and output switch, right? Well, in what I've written in blue, my input here is 1, my output here is 1. My input here is 2, my output here is 2. My input here is 3, my output here is 3. So all a logarithm is a different way of writing an exponential expression, okay? It is written differently. It's written as an inverse. Notice over here is the same idea. 3 to the power of 4 equals 81. 3 to the negative 2, that is 1/9. And 3 to the 0 is 1. So that's how we're getting these, because we understand how to do powers with exponentials, okay? Same thing over here. 10 to the power of 3 is 1,000. 10 to the power of negative 1 is 1/10. And 10 to the power of 0 is 1. Over here, 5 to the power of 1 is 5. And 5 to the power of half, we know that that's square root 5, because that's how you define a fraction like that. 1/2 is square root. And so you can see the connection between all of these. So if you're converting between exponential and logarithmic form, what are you doing, right? If I gave you log base b of a equals x, how would that look like in an exponential form? Again, I encourage you to pause the video and actually really think about it. Use the letters a, b, and x to write an exponential equation. Okay, well, the base is b. Notice every time I've been doing, I do b to the power of x equals a. So it's b to the power of x equals a. That is what the pattern has been, okay? And these are exactly the same thing. It is the same idea. It's just expressed or written in two different forms, okay? And so we use logarithms to do that. Okay. And so that's your intro to logs. That's what these little expressions mean, okay? I'm going to ask you constantly throughout these next 3 weeks to evaluate logs by hand, and you can do that by converting to exponential form to help, okay? So next up is a convert between forms practice. I gave 5 minutes for this in class. I do recommend pausing a video, trying this for 5 minutes, but I'm just going to go through the solutions here, okay? If you continue to convert to exponential form, I've given my log here. My base is 2. So this is 2. The exponent is the output. The output is 5. So it's 2 to the 5 equals my argument, which is x. Oh, before I proceed, I should probably say that. I'm sorry. B is called the base. A is called the argument. And x is called the exponent. And incidentally, it's kind of nice that x is the exponent, right? X is the exponent. That's just a linguistic coincidence right there, okay? It's nice, though. It's nice that these 3 letters correspond with things in English that make sense. Okay. Now I'll do this over here. The base is 3. Now I want to convert to a logarithm. So I say it's logarithm base of 3. The input of a logarithm is the output of the exponential. So the output was 8. So my input is 8. Equals, and now the output is the exponential's input. The input was 2x. Okay? All right. On this next one, number 3, this one was just a little tricky because in order for you to use this conversion, right, this logarithm needs to be isolated. this exponential needs to be isolated. When I say isolated, I mean you need log base 2 of, let's say, 5, right? If you have a 2 out here and you have like a plus 7, you need to get rid of the 7 and you need to divide by 2 to isolate it. So I'm going to add 3 to both sides here so that I get 10 to the x minus 2 equals 3. Now you can convert to log. It is log base 10. I don't actually have to write the 10. Of the argument is 3, and the exponent was x minus 2. Okay, that's the equation there. And if I go to the next one, this is supposed to equal 0. That was a typo when I wrote this up. I'm going to subtract 5 from both sides. So natural log x equals -5. This is like saying log base e of x equals -5, right? Because natural log has a base e. So this converts to e to the power of -5 equals x. Done. Okay? And that is just some practice converting between the forms. You're going to get a lot of this practice in the coming weeks. So if it's not sinking in yet, don't sweat it. You'll get it with time. Okay? All right. Now let's graph these things. So we want to graph the function y equals log base 3 of x. Okay? Well, how could we do that? Well, if you really understand what's been going on, you can plug in smart choices for x because you have that strong understanding and you can find pretty points. So for example, log base 3 of 9, right? Why did I know to choose 9? Well, because 3 squared is 9. So then 3 squared is 9, which means the exponent was 2. So you could put in this table 9 comma 2, all right? You could do that, and that would be fine. However, I understand that kind of thinking takes time and it takes practice. I encourage you to try it now, but I'm going to show you another method to generate a list of values that is a little bit easier if you're struggling with generating those values on your own. Okay, so let's, we know we can graph exponentials pretty easy, right? We did that previously over here. So if we can use this conversion to exponential form, then that could help us out. So look, if we say that y equals log base 3 of x, right? That's my f of x. So what if I wanted to find f inverse, right? F inverse x equals what? So how do we find inverse functions? Well, you swap x and y, right? Swap x and y. And then we'll solve for y, right? So I'll say that this becomes x equals log base 3 of y. Now, if you convert this so I say convert to exponential form, then, well, the base is 3, the power is the output x, and that equals y. So your inverse function, f inverse x, equals 3 to the x, okay? Now, 3 to the x, isn't that easy to graph, right? Can't you make a table for that? X and y, right? X and y, 1, 2, 3, 4, 5. We can make a table for this and find a few values for x and y pretty easy. I'm going to do the classic -2, -1, 0, 1, 2. Okay, just plugging those in. I'm not going to take too much time on this. If you plug in -2, you should get 1/9, then 1/3, then 1, then 3, then 9. Now, that is the table. This is the table for f inverse, right? We want the table for f. This is f, not f inverse. How do we do that? We swap x and y. You swap the table values. So it's actually now 1/9 -2, 1/3 -1, 1, 0, 3, 1, 9, 2. Notice I said earlier that you can do log base 3 of 9 equals 2, and that is true. So if you understand how to evaluate this, you don't need to do this inverse function process. But if you're stuck with it, you could find the exponential equation, and you can use that to generate the points very easily. Then flip all those values you found your table for log. Okay, so let's plot these. 1/9 comma -2 is about right here. 1/3 comma -1 is about right here. Then I got 1 comma 0, that's right here. 3 comma 1 and 9 comma 2. And that is our logarithmic points right there. Now, if I were to connect these things, I want you to notice the same pattern that we do with exponential, right? If you were to keep going backwards here, you get 1/27th, and then you get 1/80 over 1, right? 1 over 81. That same pattern is going to work up here, right? And the y value is going to increase, or sorry, it's going to decrease. It's going to go down, and it's going to go down forever to infinity. But your x values are going to keep decreasing, but never hit 0. So, incidentally, we have an asymptote here at x equals 0. The same reason you have an asymptote for your exponential function that's horizontal, you're going to have an asymptote that's vertical for logarithms. So this logarithm is never going to touch 0. Okay? So I'm going to connect this curve. Oh, I don't like that. Here's what I'm doing. Let me sketch this. I'm sorry. I want to make this nice and pretty. I'm going to make these points a little bit fatter. Okay. I'm going to sketch. Sorry, I just want to make a nice, pretty curve. Look at that. Oh, that's so nice. That's so pretty. That was ugly. There we go. Just want to make the arrow nice. And I'll sketch this down like this. Again, it is approaching but not touching the vertical asymptote. Okay? And that is your logarithmic function. All right. Notice our features. The y-intercept, we have none. The x-intercept, incidentally, is 1 comma 0. Okay. My domain. Ooh. If you read your graph, it's starting at 0, right? It's starting at 0 and it's going to infinity, but it's parentheses because it's not touching. So this domain is 0 to infinity, and your range is all real numbers. So again, we could write this as x is greater than 0. We could say that y is a real number. And that's the logarithm. That is what a graph of a log looks like. I can't really show you on the iPad, but if you can imagine rotating this 90 degrees, you could see that this looks just like this curve. It's like it's flipped on its side. In particular, it's flipped diagonally over the line y equals x, but whatever. Okay. Boy, we've been doing a lot. We're almost there. We just need to get through example 2. And then this last example, well, I was actually going to save that for the next class, but I'm going to just go ahead and do it in this video anyway. This video is just going to be long. Sorry. Thankfully, this wasn't an assigned video, right? You just got to learn this in class. Okay, let's graph the function. F of x equals log base 3 of x plus 4 plus 2. All right. Well, notice my transformations. The input here, that's my input to the logarithm. It's x plus 4, so that's a shift left 4. And plus 2 would shift up 2. It's on the output. So you could, and since there's no stretching here, you can actually just take all of these values here and shift them like this. But I'm going to, again, just go through it one more time on how to find the inverse function on all that business, okay? So I say that y equals log base 3 of x plus 4 plus 2, right? And that's f of x. Now, we want to find the table for f inverse x, right? So I say to find f inverse x, swap your x and y and solve. So actually, we are kind of hitting a little bit of 10.3 here because we actually are solving using change from exponential to logarithm. So here's what this looks like. I'm going to get x equals log base 3 of y plus 4 plus 2. I'm going to isolate the logarithm, so I'm going to do x minus 2 equals log base 3 of y plus 4. And now I'm going to change to exponential form. Okay, we're going to change this. So the base is 3. The exponent is the output, x minus 2. And the answer was y plus 4. And so if you take this, okay, you get, let's subtract 4 from both sides. You get 3 to the x minus 2 minus 4. That means f inverse of x equals 3 to the x minus 2 minus 4. And now we can generate a table of values for this. Okay? We can generate a table of values. So plug in things for x. So I'll say here's my x and here's my y. So 1, 2, 3, 4, 5. Okay. Let's plug in. Remember how I said doing whatever makes the exponent 0? Let's try 2. So now it's 3 to the 2 minus 4. That's 3 to 0. That's 1 minus 4. That's negative 3. So 2 comma negative 3. Oop, I'm sorry. Don't graph this, Mr. Spake. I'm so sorry. Let's not graph this yet. Because we're not graphing the inverse function. We're graphing log, the original, right? Now let's do 3 to the 3 minus 2 minus 4. That's 3 to the 1 minus 4. That's negative 1. So 3 gets us negative 1. And then 3 to the 4 minus 2 minus 4. That's 3 squared minus 4. That's 9 minus 4. That's 5. So when it's 4, the output is 5. Now look, that's 3 points, which means it's sufficient. I've told you my expectations are to find 3 points and then you can graph. I will find the other 2, but these are good. These are 3 solid, pretty points. And if you know where that asymptote is, you are fantastic. You've done a wonderful job. You don't need to find any more. Okay? I am, however, going to get these other 2 values here. And it's going to start looking nasty here, just so you know. If you plug in 1, you get 3 to the 1 minus 2 is negative 1 minus 4. You see this is 1/3 minus 4. That's negative 3 and 2/3. That's what that is. That is negative 3 and 2/3. I told you, I know, I said never write it that way, and now I'm going back on my own word. If I plug in 0, it's 3 to the negative 2, which is 1/9 minus 4, which means it's 3, there's a negative 3 and 8/9. Negative 3 and 8/9. And so there that is. Okay? All right. Now that you have all these table values, flip them. Negative 3 and 8/9, 0. Negative 3 and 2/3, 1. Negative 3 and 2. Negative 1 and 3 and 5 and 4. Now look, it's sufficient to have just those first three, but this will give us a really accurate picture. Almost at negative 4, right? Almost at negative 4 is 0. So we found our x-intercept there. Negative 3 and 2/3, it's at 1. So about right. Ooh. Oh, man. Okay, to be super accurate, it's more like this and then like that. Those are really like my 2 points here. Okay, and then negative 3, it's at 2. And then at negative 1, it's 3. And then at 5, it's 4. Cool. Now, where's my asymptote? Well, if you remember, the original asymptote is here at 0, right? And I've shifted this left 4. So your vertical asymptote is at negative x equals negative 4 because you shifted it left negative 4. And you can kind of see that in the table too. The x values are getting really, really close to negative 4, but not touching. And so this is my logarithmic curve. I'm going to draw a nice little sketch like this. Like so. Let's just approach this downwards like that. Boom. There is your logarithmic curve. Okay? Beautiful. Absolutely stellar. And so let's analyze some of these features. The x-intercept, well, we found that it's negative 3 and 8/9 and 0. Now, I really don't like writing that as negative 3, 8/9. I'd rather write it as, what is that, negative 35 over 9? Whatever. I'd rather write that as an improper fraction, but I don't care. It's fine, okay? It's sufficient. It's the same point. I don't care. I won't be picky. My asymptote is at x equals negative 4. My domain is from negative 4 to infinity, where x is more than negative 4, okay? My range is all real numbers. And my y-intercept, well, it kind of looks like my y-intercept is about right there, right? A little bit above 3. But you know what? I don't know. I don't know what the y-intercept is. If you really want to know, say, well, I could know with a calculator. You say, how could you do this, Mr. Spake? Well, if you say, so a y-intercept happens when x is 0, right? Or, yeah. A y-intercept happens when x is 0. So when x is 0, then it's, you say y equals log base 3 of 0 plus 4, because it's x plus 4. 0 plus 4 plus 2. So y equals log base 3 of 4 plus 2. If you use a calculator, I'm going to say use calculator, you can actually find that. So, or actually, I'm going to go to Desmos and type in, you can do it in a graphing calculator. I'll show you this in class too. Log base 3 of 4 plus 2. About 3.26. Is about 3.26. So y-intercept is roughly 0, 3.26. Okay? Now look, if I'm making you graph these by hand without a calculator, I'm not going to ask you to give me the y-intercept. If I do give you a calculator, then you can find it. Does that make sense? You can't figure out what that approximation is unless you have a calculator. You're not going to learn how to do logarithms by hand. Heavens, no. I don't think I even know how to do that, actually. I don't think I have a clue. Not when it's something complicated like that. Okay? It's a waste of our time. We don't need to do that. Okay. Done. And that should be the end of the video, except we still have one more thing to do. All right. Last thing. Boy, this is a long introduction to exponentials and logs. But I think you'll find that this is going to be the longest video in all of these. I sure hope so. I think this is the longest video of all of them because it's the most jam-packed with both information about exponentials and logs. Very important things. Okay, so one thing we're going to be experimenting with in this unit is rewriting exponential functions, which is you're going to play around with them. You're going to have fun, okay? We're going to manipulate an exponential expression into something simpler or more desirable. So this is just for fun. Rewrite the exponential function f of x equals 27 times 1 over 9 to the x, such that a is 1 and b is a positive whole number. We'll then identify the parent function and state its transformations. So here's the thing. You have to know your powers. Otherwise, you won't recognize what's going on here. So I'm going to say notice, I'm going to put a little asterisk, 3 cubed equals 27, and 3 to the negative 2 is 1 over 9. So you can rewrite f of x, you say 27 times 1/9 to the x, right? Well, if you use base 3, because that's a common base, right? That's 3 to the power of 3 times 3 to the power of negative 2 to the x. And now if you use your exponent rules, this is 3 to the power of 3 times, when you raise an exponent to an exponent, you multiply the exponents. So it's 3 to the negative 2x, okay? And now that I'm multiplying them, I could say I add the exponents. So it's now 3 to the negative 2x plus 3. That is the simplified, or I should say, it's not so that it's simplified, it's just written a different way, right? It's written with a base of 3. And now I can analyze my transformations, if we like. Now, do be very careful here, okay? So f of x equals 3 to the, now I'm going to show you something here. When we do f of b times x minus c, to know that shift c, you have to factor out b. So careful here. You're going to factor out a negative 2. And then, so this is x. So negative 2 times x is negative 2x minus 3 halves. That's what's going to get you the shift, okay? So what are my function transformations, right? You say that b equals negative 2. And when I say b, I'm not talking about the base. I'm talking about b x minus c. That whole business, right, from transformations. That tells me it's a horizontal reflection. Horizontal reflection. It's also a horizontal Is that a stretch or compression? Do you remember? Well, I think it's compression. Okay, and then C equals negative 3/2. Actually, it's not 3/2, it's positive 3/2 because it's x minus C, right? So it's C equals positive 3/2, means it's a shift right 3/2. Okay, now let me tell you, I'm not going to be super picky about function transformations in this unit. We've already done that. We did that in Unit 1. I'm really just doing this as a boomerang to help you remember those transformations because they're important and they help you analyze functions in different ways. But really, all the new skill I care about here, that we care about here, is developing this way of manipulating exponentials to make it look like something more familiar. And so those are the transformations. On the parent function, you say parent is 3 to the x. Okay? Now, is it a growth or decay function? Well, I would pause the video and actually give this question some consideration. But if you look at the original function, y equals a times b to the x, right? Well, this is a simple algebra 1 function, right? b equals 1/9 means b is less than 1 but greater than 0, right? b is between 0 and 1. So it is exponential decay. All right? Because this is my y equals. So this get that. So it's exponential decay because b is 1/9. But what if you were given, right? I say, what if given y equals 3 to the negative 2x plus 3? Well, how could you know that it's exponential decay? Well, so the base is 3 means the parent function, right? So parent function 3 to the x looks like this, but new function 3 to the negative 2x plus 3, it's shifted, right? We said it's a horizontal compression and it's shifted right, but the really important imagery here is that it's a horizontal reflection. So it's actually going to reflect horizontally because horizontal reflection. So it is exponential decay because it's a horizontal reflection of parent 3 to the x. And so that's how you'd know that. Okay, now that's just kind of a thought, a thinking thing. Okay, you're just thinking about it. To really connect all this knowledge together, to really tie the thread through everything. So if you're looking at the original, the base is smaller than 1, so it is exponential decay, done. But if you were given it rewritten in this certain expression of function transformations with a base of 3, compare that to the parent function 3 to the x, and notice that because of it's a horizontal reflection, it's going to change it from a growth to a decay because you've flipped it horizontally. And there it is. Okay. This was a lot I hope it was helpful. Wow. I have no idea how I did that in class before the bell rang. That's incredible. Okay. Hope you enjoyed the video. Thanks for sticking around and watching, and I hope that you got a really strong understanding of both of these things. Exponential form, logarithmic form, finding inverses, graphing, all that. We covered a heck of a lot in this video. Okay? Take care, stay healthy, and I'll see you around.